All right, so continuing our work into further integration. This lesson is the reverse of the chain rule. The chain rule allows you to differentiate a composition of functions. This allows you to undo that. This is also, much of the chain rule is quite important. This is quite important for integration. Although we're limited, don't think this works on everything. And part of one thing that makes integration challenging is there are less clear-cut methods to integrate things compared to differentiating. As well, like so many other things, this is a lesson that's really hard to just explain without doing it. And the more you do it, the easier it gets. I'm not going to say it becomes easy, but definitely practice is especially important here to get a feeling for it. Because quite often you have to develop a feeling, and the feeling is to think, okay, what is the inside function, or what was the inside function, or what is the phrase we have here is the innermost function. And that is sometimes not so clear. So I want to integrate this. I want to find the antiderivative of this, essentially. And what we learned from the previous lesson is not going to work because there's this, it's a product really. I have 12x times the cosine of 3x squared. So what I want to do first, as soon as you realize that we can't just integrate it really quickly, is I need to think about what's my inside function. And we generally, again, it takes a matter of practice to get a feeling for it, but we look for what's on the innermost. In this case, it seems like 3x squared. And if sometimes we try it, and we'll see if it works or not, and we call that u. So I'm now going to say, let u equal 3x squared. Why u? I don't know. It's just what we do. It rhymes. It doesn't obviously have to be u, but I think it helps be conventional here. So I'm going to think of that as my inside function. I now want to differentiate this. So I now want to find du dx. That's pretty nice. It's just 6x. I now want to isolate just the du. Now you can imagine multiplying both sides by dx, which at higher levels is a bit of an issue with that. Right now it's all good. And so imagine multiplying both sides by dx, or isolate du, and you get du equals 6x times dx. All right. So what do we do here? Well, let's go back. I want to take my original question. I want to write it as an indefinite integral. So 12x times the cosine of 3x squared dx. All right. Well, already I said 3x squared, I can substitute for u. So I'm going to take that right now and save myself a bit of time and just put a u here. Our goal, though, if we've integrated, if that u is the correct inside function, our goal is to use this right here to substitute out all our x's and have only the variable u. Now notice, what do I have here? I have 6x times dx. Well, there's the dx. I have 12x here, not 6x, but it's almost there. So imagine if I take that 12x, I'll leave it like this for now, and I write it like this, as the integral of 2 times 6x times the cos of u times dx. Notice I have dx times 6x. And what I see there, 6x times dx, is the same thing I see here, which means I can substitute that with u, which means everything I have in green here on the right-hand side, I can write as just du, which means I can write this now as just the integral of 2 times the cosine of u times du. And remember, u is 3x squared. All right, now I have rewritten through substitution, hence it's called integration by substitution. I've rewritten my integral in a much simpler form. I can integrate this quite nicely. And so this is going to be 2 times the antiderivative of cosine, which is sine of u plus my constant. Now that's it. Might seem like we're done, but don't forget there was no u in my original function. So all I need to do now is go back and replace u with 3x squared, and I'm done. So the integral is 2 times the sine of 3x squared plus my constant. And I'm done. Now, if you're not sure, I can go back and double check. And you would differentiate using the chain rule. And I differentiate the outside function first, which is sine, and multiply by the derivative of the inside function. And you should end up with this. All right. And so let me talk about how you can tell if we didn't pick the right inside function. Let's say if we pick something wrong, we wouldn't really notice it until we get to this stage right here, and we'd find that no matter what we do, there's no way of substituting this for this. There's no way of making it work. The hard part is sometimes there is a way, it's just not as obvious. But if it really is no way, then we got to find another way to substitute it. All right, that's it. Let's look at this. Okay, so I want to integrate this. I got a fair amount going on here. If we, it's hard to tell what our innermost function is, but I'm going to go with x squared plus 1. So I'm going to say let u be x squared plus 1. That means I want to now differentiate that with respect to x, so I get just 2x. I want to isolate the du, so I get du equals 2x dx. All right, so let's look back at what I have with the integral here. So I have the integral of x times dx, and in my denominator just have a u. All right, let's see how these things compare. I have x dx, I have x dx, but I have this extra 2 right here that doesn't exist here. I kind of need there to be a 2 right here so that this all works. Because if I have a 2 right there, then suddenly I can just substitute that for all du. Well, the idea is I can put a 2 there as long as I balance it out. So if I'm just going to put a numerator of 2 there, I need to put a denominator of 2 here to make it cancel out. Or what we usually do is just multiply this by a half, or put that 1/2 outside the integral, right? It doesn't really matter. I can also put it out here. Lots of options, right? Maybe I'll stick with this. But that 2 I see there wasn't there before, but I needed to create it. And in general, you can add any constant you want as long as you just immediately cancel it out. If you want to multiply by 2, sure, just divide by 2 or multiply by a half. And now, if you look at everything I've highlighted in green, that's identical to du. And now things are going to come together quite nicely. So I can write this as 1/2 times the integral of just du over u, or just 1 over u times du. And now I can realize from previous lessons, this is going to lead to the natural logarithm. So this is going to be 1/2 times the natural logarithm of the absolute value of u plus a constant. That's it. Don't forget u is actually 2x squared plus 1. So my answer, my final answer is 1/2 times the natural logarithm of the absolute value of x squared plus 1 plus c. Keep in mind, if you have time, you can always use the chain rule and go back. Keep in mind, on a test, you probably won't have time. Quick thing I'll mention, in general, anytime you notice you have an integral where your numerator is the derivative of your denominator. Now, in this case, it's not quite. The derivative of x squared plus 1 is 2x, not x. But anytime you notice that, or something similar, you're probably going to come back to the natural logarithm here. And in general, for example, if this really was a 2 there, if that was the question, then as soon as you notice that, hey, my denominator, if I differentiate it, is exactly my numerator, then you could just go you know what's going to be the natural logarithm. And that idea is what's kind of mentioned right here. Anytime we're integrating where we notice the derivative in the numerator and, whatever is in the denominator, its exact derivatives in the numerator, then we know we can just go straight to here. It just speeds it up a bit. And as we've noticed in IB on assessments, sometimes if we can speed certain things up, it gives us a lot more time to focus on more challenging things. Either way, though, I'm done that one. All right. Let's look at this. I want to integrate the tan of x dx, but just where x is between 0 and pi over 2. We'll get to the 0 and pi over 2 part in a bit. First, let's look at this and realize, okay, that means if I can write this as the sine of x over the cosine of x dx. All right, well, notice, similar to before, my denominator, the derivative of cosine, is not sine, it's minus sine. But that alone tells me that my answer, the natural logarithm, is going to come into play here. However, it's not an exact, my denominator is not exactly, my numerator is not exactly the derivative of the denominator, so I'm just going to go back to this. But that gives me a sense that, okay, let's make u cos x. That means du dx will be minus the sine of x. Multiply both sides by dx, you get du equals minus sine x dx. All right, so now if I look at what I have here, sine x dx, that's right there. I just don't have that negative, but I need to create a negative. So again, like I said before, I can squish in a negative there if I just squish in a negative here. Negative times a negative is a positive. And now, if I look at what I have here, everything highlighted in green is equivalent to du. Everything highlighted in blue is equivalent to just u. So I can now write this as minus the indefinite integral of 1 over u times du. And now I can see, yep, this is going to lead me to an antiderivative involving the natural logarithm. So I have minus the natural logarithm of the absolute value of u plus my constant. Let's take u and put it back to cos x. And it seems like we're done, and we're almost done. However, now don't forget there was a restriction on x at the beginning. It said here that x was only between 0 and pi over 2. Well, let's think about cosine when x is between 0 and pi over 2. The cosine of x is always positive when x is between 0 and pi over 2. In terms of degrees, 0 and pi over 2 is from 0 to 180 degrees. And in between 0 and 180 degrees, cosine always gives you a positive value, which means in this region here, the cosine of x right here will always be positive, which means we don't have to actually deal with those absolute value brackets. So a slightly simpler answer is just minus the natural logarithm of the cosine of x plus a constant. We don't, in this case, need the absolute value because we know between 0 and pi over 2, the cos of x will never be negative. All right, last one. This one relies on learning or using an identity that was brought up very briefly in the last notes, but I don't think we actually used it. It's not actually technically part of this course. It really should be. And I'm going to go back a lesson here. And it's right here. It's what we call the double angle identity for sine. There's countless identities in trigonometry. This one here is not actually part of the curriculum, which is kind of wrong. And to some extent, my fear is they may expect you just to know it anyways. And it's not difficult. In general, the sine of 2x is always the same as 2 sine x cos x, and vice versa. And there's also a double angle identity for cosine. The cos of 2x is always the same as this. However, this one here is going to come into play for this question here. And if you're not familiar with it, I would recommend memorizing those two identities. Let's go back to the actual question at hand, though. All right, I want to integrate this, and it's perhaps the most challenging part is what's my inside function. Well, if I look here, the derivative of cosine, it does relate to sine. It's not sine 2x, but let's just try making that my innermost function. So let u equal 1 plus the cosine squared of x, which means du dx is the derivative of 1 is 0. The derivative of cos squared x is 2 cos x, but use the chain rule. The derivative of cos x is sine x. And so multiply both sides by dx, or isolate du. Du in this case is 2, I'll write it like this, sine x cos x. I'm writing it in this order because I know that's the double angle identity for sine. I recognize that. And I go, hey, what you see there is the sine of 2x. And so let me go back to this original question. I'm going to rewrite sine of 2x as, using the double angle identity for sine, as 2 sine x cos x. And I'm going to rewrite 1 plus cos x squared as just u, because that's what I substituted it with, times my dx. So notice now, everything I see in green on the one side relates to the other. So I can now rewrite this as the integral of 1 over u times du. Oh, that's so lovely. And so I can now integrate this, and this is the natural logarithm of the absolute value of u plus a constant, and that u, of course, is 1 plus cos squared, not cos squared x. So that is inside the absolute value, which is inside my natural logarithm and has a constant added to the end. All right, with that said, Is there a way of integrating this without using that identity? Yeah, for sure. How do I do it? I don't know off the top of my head. And just keep in mind, there's always more than one way. Although I don't think you can integrate anything by integration by substitution. But this does cover a fair amount of things. And that identity that I use right here to here, I would recommend you memorize that. Even if it's not officially part of the course, because no matter what, it gives you more options. And it makes this actually a pretty quick question to do then.